Autonomous vehicles are no longer just a concept. They are rapidly moving toward everyday reality. In the coming years, we expect them to be widespread on our roads, bringing opportunities to make transport systems safer, more efficient, and more sustainable. They can react faster than human drivers, follow predictable paths, and operate with much greater precision. This means less congestion, low delays, and more reliable traffic network overall. But how should these vehicles manage intersections? Many existing approaches assume continuous communication between vehicles or with infrastructure. While this sounds powerful, in practice it creates risks, communication failures, cybersecurity concerns, and reliance on expensive infrastructure. We believe the future is communication free. Each vehicle should be able to rely solely on its onboard sensors and local decision making. If every autonomous vehicle can act independently, yet consistently, then we can achieve safe, scalable, and efficient traffic control without traffic lights or central managers. This vision is what motivated our research. Hello, my name is Ali Reza Soltani from the University of Sydney. I am presenting our recent work developed together with my supervisors David Levinson and Mohsen Ramezani. Our paper is titled Communication Free Distributed Control Algorithm for Autonomous Vehicles at Intersections, published in Transportation Research Part C in 2025. In this presentation, I will explain how autonomous vehicles, without relying on traffic lights or even direct communication, can still manage intersections safely and efficiently. Centralized signal-free methods often rely on heavy communication and complex optimization. While they work in low or moderate demand, they struggle at high demand near capacity. In congested conditions, traffic signals can actually outperform them because signals discharge vehicles in platoons, which boosts throughput. Our approach is designed to overcome this limitation. It reduces delay while also being capable of handling congested traffic, combining the benefits of distributed decision making with the efficiency of platoon-like discharges. What if autonomous vehicles could manage intersections entirely on their own, without traffic lights, and without any communication at all? It's not extremely hard to imagine a communication-free distributed system, where each vehicle simply looks around and tries to find its own fastest feasible path through the intersection. This works to some extent, but the lack of broader information quickly becomes a problem as traffic demand rises. Vehicles may act too individually, slowing everyone down. For a system to succeed, we need both safety and comfort for users, and at the same time efficiency for the whole network. The goal of our work is to design an algorithm where vehicles behave more altruistically. They still act independently, without digitally sharing data, but they also take into account the delays of others when making their own decision. The key to optimizing delay at intersection is the overlap in how long vehicles occupy conflict zones. By minimizing this overlap, we directly improve system efficiency. The CfDCA frames the intersection as a resource acquisition problem. Each conflict zone, where vehicles' path may cross, is treated like a shared resource. Vehicles use their position and speed to decide whether they can safely acquire that resource. And because all vehicles independently build the same graph, they reach consistent, distributed decisions without any communication. Our method has several unique features. Vehicles are first classified into zone-based subsets: observation, buffer, and active sets, which structure how they approach the intersection. The system then adapts dynamically to traffic inflow, behaving differently under low demand and high demand conditions. Safety buffers are built in to guarantee clearance time, while a tolerance function prevents vehicles from waiting too long. And finally, a strict priority ordering ensures that deadlock can never happen. In this example, we see the CfDCA operating under low demand conditions. Vehicles approaching the intersection detect others within their sensing range and classifying themselves into observation, buffer, or active sets. Those in the active set are the ones closest to the intersection, and they are eligible to acquire the conflict zones they need. The decision is made based on a priority function, which accounts for both distance and speed, so that vehicles with shorter time to intersection are getting higher priority. As a result, each vehicle makes its own acceleration or deceleration decision locally, without communication. This ensures a smooth crossing with minimal delays, since conflicts are resolved quickly and vehicles keep moving whenever possible. Now we look at the CfDCA under high demand conditions. More vehicles are here, and observation area is dense with conflict zone requirements. The algorithm recognizes this and switches to high inflow mode. In this regime, vehicles in the buffer set are held back before the intersection. Instead of immediately requesting conflict zones, this prevents oversaturation, reduces conflicts, and allows the vehicles already in the active set to clear efficiently. The system naturally forms platoons, group the vehicles crossing sequentially, similar to how traffic lights discharge queues. This platoon effect maximizes throughput while still keeping the system fully distributed and communication free. Even in congestion, the algorithm balances safety, fairness, and efficiency, ensuring progress without deadlock. Our results show clear advantages of the CfDCA. Looking first at average delay, the green line shows our method consistently achieving lower delays than both actuated signal and first-come first-served, especially at high inflow rates near capacity. When we compare queue length, we see the same trend. Across all turning movements, CfDCA maintains much shorter queues compared to signalized control. This means a smoother flow and reduced congestion. Finally, even when we introduce realistic measurement error, the system remains robust. Delay increases only slightly and safety is not compromised. Altogether, this result demonstrates that CfDCA is both efficient and reliable under a wide range of conditions. Our results show that autonomous vehicles can manage intersections on their own, safely and efficiently. This opens the possible of future cities without traffic light, with a smoother traffic, lower delay, and higher throughput with no need of constant communication. Thank you for watching. If you'd like to explore the details, please read the full paper using the QR code on this slide. And feel free to reach out to me at alireza.soltani@sydney.edu.au. I'd be happy to continue the conversation.